so we can start. All right, so today we'll, in the last lecture we were looking at some things that were, some things about diode which were not maybe dealt with in a proper manner in many of the books and places. And we will look at one aspect of the diode in a little bit more detail today. But what I want to introduce you to a approach of studying various concepts and mechanisms using what are known as causal diagrams. Causal diagrams. So at lots of places we deal with questions of why does something happen in a certain manner, or how does something work. For example, how does a common emitter amplifier, how does it amplify? Or how does a common source amplifier amplify? Or how does a differential pair work? So you deal with questions like this, and so you're dealing with mechanism, right? You're dealing with a mechanism behind the operation of a circuit or a device. And you will find that these causal diagrams can be quite helpful in understanding these mechanisms. So let me illustrate to you. For example, in a way we, for example, when I said why does, for example, we have why does delay occur? Why does delay occur in a device or a circuit? Right, so the question was why? Why does it occur? Why is there a delay in a device or a circuit? And we drew a diagram like this. And in this form, as I said, so what you're looking for, any device, what you're doing is you're causing a change in current. And we said and the change in current is being caused by a change in voltage, right? And what is the mechanism? Why does a delay occur? So we said there's an intermediate step here. Delta V causes a change in charge, and charge causes a change in current, right? We drew what causes what, right? Delta V. So when I draw an arrow like this, I'm saying, and I put a plus. So for example, it could be a change in, let's say, diode voltage. If you increase the diode voltage forward bias by a certain amount, what it does is it increases the charge. For example, the whole charge stored in the, if I'm drawing a P plus N region here, then what happens is the electrons injected in this particular region increase. And then this delta QP then causes a change in current, delta ID. So that's the mechanism of operation of a diode. A change in voltage causes a change in charge. A change in charge causes a change in current. And we said, well, this then, if we look at this, so this is a causal diagram. It describes what causes what. So delta VD causes a change in delta QP. So when I draw an arrow, it says delta VD causes delta QP. And when I do a plus here, it means an increase in delta VD will cause an increase in delta QP. If I had drawn a minus here, then it would have implied that increase in delta VD would have caused a decrease in charge, minus of that. Okay, so in this case it is plus. And so what we are saying is this relationship is nothing but there is a capacitance involved here. Delta VD causes a change in capacitance, and then we said the capacitance then has to be charged and discharged, and there's a finite amount of current available for charging and discharging, and that's the reason for the delay. Now, if you draw a diagram like this, if somebody asks why is so this is the mechanism of operation of a diode. Why is the diode characteristics exponential? What is the reason for it? The reason for it is the first step. Is the exponential relationship between the charge and the voltage. That we have been drawing this. For example, if we've been drawing this, that there's a depletion region here. And at the edge of the depletion region is what is injected, delta P, let's say 0. This is exponential. So the exponentiality of the diode's characteristics comes from this particular step here. That's where the exponential, it's not here. There are two, if you would like, there were two steps in diode's behavior here. An increase in delta V, what it does is increases the hole density here. And then these holes diffuse and recombine and all that and give rise to a current here. Anyway, so let's look at this causal diagram in a little bit more detail with more examples, and then we'll come to our point here. So if let me start with, so this is something that we have already looked at. Let's look at a different example. Let's look at an example of a, let's say you're doing amplifiers, so let me take a common source amplifier. So common source amplifier, if I were to draw, very simple, that all of you are familiar with. Right, V0. Right, this is a bias voltage here. And this is a signal that you're wanting to amplify. So how does the common source amplifier, I just jotted down some things for my own this thing here, so that's why I'm looking at the mobile. I'm not I'm not scrolling and surfing. I'm looking at the what I've for my own this thing to keep myself on track. Okay, so how does the amplifier how does it work? Somebody asked, how does a common source amplifier work? So how, the question that we are asking is, how does this amplifier work? Right, so the question of how, you're looking for a mechanism. And when you're looking for a mechanism, you're saying this causes this, causes this, causes this. Eventually, what are you looking at? You will start with Vs. Right? You start with Vs. And then what you're looking for is V0. Right? An increase in Vs causes a much larger increase in V0. Now, how does the signal travel from Vs to V0? What happens? What do you think happens? We are wanting to draw a causal diagram. In between, we would like to have some intermediate variables, which shows how the signal goes from one end to the other end. So what does Vs do? So that eventually, see, note that what we are looking for is, what is this mechanism? How does it go and change V0? And not only change V0, but change V0 by a larger amount. Right? How does it happen? What are the intermediate steps? What would you say? Vs does what? Look at the operation of this amplifier. What does Vs really do? Vs causes a change in VGS. So what I would do is, I would put an arrow here and draw a VGS first step. And so I'll put an arrow that Vs causes a change in VGS. And note that I'm using small signal quantities, small VGS. Right? So Vs will cause a change in VGS. And what kind of a change does it cause? Will it cause VGS to increase or decrease? And so when I write something inside the circle, I'm assuming that Vs is increasing. So increase in Vs will cause increase in VGS. So I'll put a positive sign here. All right. So it causes an increase in VGS. What does VGS do then? Which current? Drain current. So what happens is VGS causes a change in IDS. Or if you would like to do it in a okay, so let's put it VGS. This causes a change in IDS, small signal IDS. All right, or maybe sometimes maybe if you would like, you can do it like this. A Vs causes a change in gate to source voltage, and it causes a change in delta, causes a change in drain to source current. And is that relationship positive or negative? Positive. And I put an arrow here. Then what does delta IDS do? How does it affect V0? This drain current flows through RD and causes a change. So I should draw an arrow from here to here, right? And what should I put an arrow? Positive or negative? Right? Negative. That's the operation of the amplifier. The applied signal causes a change in VGS. That VGS causes a change in IDS. That IDS flows through RD and causes a change in output voltage. If I'm not talking in small signal quantities, let's say I can put here delta V naught causes a change in V naught. Now so this is a causal diagram of the operation of the amplifier. So now you can see, suppose I ask the question, where does the negative phase shift come? That is 180 degree out of phase. Where does it come from? Why is there a 180 degree phase shift between output and input?
Because ID flows from drain to source.
It is this step, right? Note that this is where the negativity comes, 180 degree also. It is this phase. What is this? Where does non-linearity in an amplifier come from? Non-linearity. Amplifier is non-linear. I mean, you want it to be linear, but this is a non-linear. Where does the non-linearity in an amplifier come from? Look at all the steps. Where do you think it comes from? Note that between here, this one, this is a change in current and change in voltage is because of RD. It's a linear relationship. Where does non-linearity come? Here, between VGS and ID. So all non-linearity comes in from here. All distortion, everything will come in from here. Right? This is the source of distortion. Distortion and all those other things that are there. And this is the reason why, because it's a non-linear relationship, you say, well, I have to keep my delta VGS small. I have to keep it small and small signal and all that. This all comes from because of this part of the intermediate step, the change in gate voltage versus change in drain to source voltage. And this is where you can say which amplifier would be more nonlinear, BJT or a MOS? Which has more nonlinearity in it? Note that if I were to draw a common emitter amplifier, all that will change is, instead of VGS, I will write base emitter voltage. Instead of drain current, I would write collector current and then output voltage. So same causal diagram is there. So which amplifier would be more nonlinear? Which will have more nonlinearity? BGT, because this relationship between VGS and ID, in one case it is what? Exponential. IC goes as IS e to the power VB by VT. Exponential. In the other case, ID is beta VGS minus VT square by 2. Note that nonlinearity is a square. In the other case is exponential. So the requirement that you have to keep the input voltage very, very small is more in BGT amplifiers. You have to really keep it very small in maybe 2-3 millivolts and all that. Otherwise the signal starts looking fairly distorted. While in a MOSFET, so in a BGT you have to apply maybe 4-5 millivolts, you're okay. In a MOSFET you can go up to easily 20 millivolt, 50 millivolt and the signal still looks fine. Doesn't look so bad. Why? Because look at the relationship between the two. So all distortion comes in from here. Anyway, so drawing this causal diagram would help you understand things better. So let me draw it quickly. Common drain amplifier. CD. Common drain amplifier, right? So common drain amplifier, all of you are familiar, like this. And maybe you can add there's a load here, RL and all that. And you have to bias and apply a voltage and all that. Right, so VS. So in this case, so we start with again VS. And this is where V naught is. So what does VS do again? An increase in VS will do what? Will change will cause an increase in VGS, right? Positive, because that's where the signal is going here. Mechanism VGS. What will VGS do? Again, the mechanism will cause a change in current, positive, Any increase in VGS will always increase the current. What will this increased current, where will it flow? It will flow through this parallel combination of, let's say, RS and RL and all that. So will cause a increase in V naught. But do you see something else that is happening? Something else that is going on here. So this is also positive. So first thing that you note is that there seems to be all positive, 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 right? So there is no phase shift, 180-degree phase shift compared to the previous one, right? The output is in phase with the input. But something else is happening here. A change in increase in V naught, what does it do to this value here? Source voltage. Source voltage increases. And source voltage increases, then what does it do to VGS? Are you seeing this? An increase in V naught will cause a decrease in VGS. This feedback is there in this circuit here. Any increase in this voltage, capacitor is like a short, leave it, so will cause an increase in this, and then it causes a decrease in VGS. So there is you can see a negative feedback loop operating. What is the relationship between the VGS and IDS? You know that the relationship is GM, small signal, right? A change in delta VGS causes a change in delta IDS. What is the relationship? GM. What is the relationship here? IDS is flowing through parallel combination of RS and RL. So what is the gain from here to here? Delta VGS to delta V0? GM times? GM times. So you're seeing that this path is nothing but GM times RS parallel RL. Now I'm going beyond the causal diagram. Causal diagram is showing this thing. So if this gain is high, what do you think will happen to this delta V naught? If GM RS parallel RL is, let's say, 50. So note that a change in VS causes a change in VS and is causing a change in V naught. But then this is being fed back here. Then what do you think is likely to happen? If I make a statement that delta V naught will be almost equal to, see, this is coming here, delta V naught will be equal to Vs. The two are almost going to cancel each other. Do you think this will happen or not? Delta V naught will almost, if there is a big gain from here to here, and this is coming back and subtracting from it, there is no other possibility except that the two are very close to each other. Just think about it. I'll leave it for you to argue and show that this is true. Delta V naught is almost equal to delta Vs. With some, you can put in some numbers and things like that and convince yourself. So this is the reason why you are saying is that this is also called as a output voltage follows input voltage, and you are seeing a gain of 1. Gain of 1. Delta V naught is the Vs, and this is also why it's called source follower and things like that. Let's look at, so think about it. We can come back if you're not able to see it or you have difficulty, we can come back to it. Let me take another example. and let's draw the together and see. To understand the mechanism, V0. Will assume that is biased properly. So will Vs affect V0? I've not applied anything here. Let's say M1 and M2. Nothing is applied on this side. Will Vs result in V0 or not? A change in input to this, will it affect the output voltage? If I put a sinusoidal input, I'm not applied anything here, note, ground. If I put a sinusoidal input, will I get a sinusoidal here? Will I get or not? On the other side. No, there's no current mirror and all that. That kind of a amplifier is not there. It's just two parts there. Do you think I'll get a sinusoid or not? Huh? No, yeah, yes or no? Who wants to say yes? So again, what we are asking is, what is the mechanism? What causes what? Build a causal diagram. Start by building a causal diagram, okay? So where do we start? So what we are looking for is how we want to see whether there's any connection between Vs and V0, right? So our starting point is Vs. Okay, so what is this Vs going to do? A change in Vs, or when you apply a sinusoidal, it will go up and down and all that, right? So what will it do? Start building the diagram. Will cause a change in VGS. Okay, so VGS1. So let's put delta. Agreed? Positive change? Correct? Positive. It increases. All right, what will it do? Put a causal diagram again, causes a change in ID1, right? It increases. All right, so note that this is ID1. Now what happens? ID1, if you now look at the amplifier, ID1 is like this, right? Flows here, straight. ID1, now where does it go? It comes here. Where does it go? No, it has two paths now. This is where you have to understand the mechanism. It can go here or it can go here. Note that we are talking about change. We are not talking about absolute value of current. So it has two paths. The current here has this path and has a path up. Now, this resistor that you normally connect is what? Is a large resistor. While you have to, as a MOSFET, you have to remember that if you, this is where the mechanism of a MOSFET is there. Let's say if I have a MOSFET. Note that we are talking about changes, small signal changes and all that. If you look from here, what do you see in a MOSFET? Resistance. Very high, correct? Okay. If you look from here, what do you see? From the drain. You see what? R0. Output resistance, right? R0. If you see from here, what do you see? From the source, what do you see? Huh? You don't see R0. The source and the drain and the source are not the same. As somebody rightly said, it's 1 over GM. 1 over GM. As an example, this could be of the order of 1 kilo ohm, and then this could be of the order of 100K. So when you are looking from the source, the resistance is fairly small. So now with that idea, note that the current has two paths. It can go down or it can go up. Where will it go? When you look into the source, the resistance is small. So this current delta ID1, this is the important part here. Current delta ID1 will not flow here, will go into. And what will it do to delta ID2? But note the direction in which it's flowing. What will it cause? So this is plus, but what will it cause delta ID2? Minus. ID2 will decrease. Now this delta ID2, it will flow where? The same in RD. So what will it do to this thing? Output voltage? Plus. There is a path. Look at the path. It will cause a change. Sorry, delta ID2 will cause a negative. So what do you think will be the phase shift first of all? No, look, plus, plus, minus, minus. So what will you get? In phase. You'll get a signal in phase. And note that delta ID1 will be equal to delta ID2 only. If I'm saying nothing will flow here because this is a larger resistance, so the relationship between delta ID1 and delta ID2 will be same, will be equal in magnitude. This is the operation of the differential pair. This is what is happening in the differential pair. The mechanism is, that's how the signal is flowing. But now if there is a delta ID2, it would require it would require, you know, that related, it would require a change in delta VGS2. There has to be a change in delta VGS2. And a change in delta ID2, whatever, this is a positive change. So note that from here you can see Vs is equal to delta VGS1 plus delta VGS2. Right? A change here plus a change here. Sorry, delta minus delta VGS2. Vs and this. Magnitude of, do you see that the magnitude of both of them will be the same? Because delta ID1 is same as delta ID2, so the magnitude is the same. So are you seeing now that delta VGS1 will be equal to half? Only half will appear. Right? I mean, this is not a course on analog circuits, so I'm not going to go into details of it. But what I'm pointing out to you is the usefulness of causal diagram. If you draw causal diagram, you will understand the mechanism of how this thing works in a better manner. You can do endless derivation, derive small signal and all that, KVL, KCL, you'll get a value of gain and all that. But this is an essential step to arrive at a qualitative understanding of how is this differential amplifier working? What is the mechanism behind it? So now you can see what the signal path is and how it is traveling. All right, so let me see if you want, you can now modify this and see what happens in a, I'll leave it to you for a, let's say like a homework problem, that if I draw a causal diagram for this one. Draw a causal diagram. Let me put a current source now. Many times current source is there. Draw a causal diagram here. How does the signal travel and affect V0? Look at the paths and how does it go. And then understand what is the difference between this use of a current mirror load versus the difference between use of a resistive load through this causal diagram. Draw a causal diagram like this and draw a causal diagram here. Okay. All right. So let's do some more causal diagrams. Okay. Today's let's spend time on this one here. So here is a again back to common emitter amplifier. Earlier we looked at common source, common emitter amplifier. So one is I'm trying to through the previous examples I was trying to illustrate to you the mechanism behind various devices and circuits. What is the underlying mechanism? And you understand that through a causal diagram. We'll come back to a PN junction. The main reason why I'm introducing this causal diagram is for you to understand why do we call current in a PN junction to be a minority carrier current? Why do we call it as a diffusive current? Why do we do that? Okay, what is the reason behind it? We are introducing this causal diagram. But along the way, there are many interesting things. So for example, here, if you look at this particular circuit, I've written, you know, you've all done GATE or you've done your undergrad, so you know this. AV equal to, I mean, basically equal to minus GMRC, right? So that's the gain of this amplifier. Ri is basically equal to R pi, which is equal to Vt by Ic times beta. R0 is Rc here, right? Well-known equations. Now, typically what happens is, okay, you take a circuit, you analyze it, you get these particular expressions, right? And as I said, you know, a lot of time is spent in deriving these equations and then calculating numbers. What is the gain of this amplifier? What is the gain of that amplifier? What is the gain of this? That's what you do. You calculate numbers, right? But some places, what you do is you try to figure out what do these equations mean. Because if you're a designer, note that as a designer, whether you're a device designer, circuit designer, or any design that you do, in any design you will encounter trade-offs. That's a feature of all design. As you're trying to maximize something, you lose something. Right? This you would always encounter. The trade-offs are there. And a good understanding of a device and a circuit means you understand the inherent trade-offs. You know what the trade-offs are there in that particular circuit or device. Right? It's not enough just to derive AV, Ri, R0, plug in some numbers and say here is the value of the gain, here is the value of Ri, here is the value of R0. Right? I mean, of what use is it? Just calculating the numbers. Eventually you become a designer and then you have to modify the circuit and you have to design for a certain gain. And when you have to do, then you will always encounter trade-offs. You know, you're working in a company, your boss says increase the gain to 500. Right? I want a customer is asking for a gain of 500. Well, you say, well, if I try to give you a gain of 500, then I will have to reduce the input resistance or output resistance or something, right? You will always encounter trade-offs. So let's see, where did you guys study this from? Which book? This basic amplifiers, basic analog circuits? Huh? David Bell. Any other book? Sedgwick and Smith, right? A very, very popular book, Sedgwick and Smith. So let me bring something from Sedgwick and Smith, right? So look what Sedgwick and Smith is doing. Let me read it for you. So he does all this calculation, right? All the analysis. Then he says, this concludes the analysis of the amplifier. This concludes the analysis of the amplifier. Now we can make following observations. We can make, now let's look at the results. We have derived these results. What he's saying is, let's look at them. What do they mean? Right? So what are the things that he says? The input resistance is moderate to low in value. Input resistance focusing is moderate and low in value. Obviously, Rn is directly proportional to beta and is inversely proportional to the collector current. Obvious. To obtain higher input resistance, the bias current can be lowered. To obtain higher input resistance, the bias current can be lowered, but this lowers the gain. This is a significant trade-off in a common emitter amplifier. This is a significant trade-off. If a much higher and all that, the output resistance R0 is moderate to low in high in value. Reducing RC to lower R0 is usually not a viable proposition because the voltage gain is also reduced. So you want a lower output resistance, but if you try to reduce R0, AV also reduces. The open circuit voltage gain can be high, making the CE amplifier. Unfortunately, the bandwidth of the amplifier and all that. So what he's talking about, the trade-offs that are there. You try to increase RI, well, you will lose gain. You try to reduce R0, well, you will lose again gain. Then there's a trade-off between gain and bandwidth and all that. So all this is being described in what? It's being described in words. Right? Now all of you have heard a picture is what? A picture is worth more than 1,000 words, right? This whole thing can be captured in a nice causal diagram. The whole thing, in fact, much more than that also can come out in a causal diagram. So rather than, so what you're looking for is, note that you're looking at the relationship between AV and RI, relationship between these, relationship between these. You're looking for relationships. So let's do a causal diagram. And okay, so let me okay, I've drawn the causal diagram again here. So let's see if it makes sense. This is the whole thing is captured in this diagram. So what is my goal? Note that in red, what have I shown? In red is what I want. I want high voltage gain. I want high input resistance, and I want low output resistance, right? These are the three things that are there: AV, Rn, and R0. What is it that I can change in my circuit? What is it that I can change? If you look at what are the variables that I have under my control: RC, IC, and maybe beta. These are the three things that you have. So these three things I've written in green, intermediate: RC, beta, and IC. Okay? And I'm now looking at how do they impact. So an increase in beta, what does it do to Rn? Look at, let's see. So these variables are clear now: IC, RC, and beta. In between, I've also defined an intermediate variable, which is IC times RC product. So note that Rn, as you know, is equal to Vt by ICQ times beta. AV is ICQ by Vt times RC, and R0 is RC. So let's see if these relationships are clear. Is this clear? Increase in IC, what will it do to Rn? An increase in IC will cause a decrease in Rn. So this arrow is fine. IC goes into Rn and causes a decrease. But IC will also do what? Increase the IC-RC product. Why am I writing IC-RC product? Because note that gain is nothing but IC-RC product divided by Vt. It depends on the product. So an increase in IC, what does it do to IC-RC? Plus. An increase in IC-RC, what does it do to AV0? Plus. Right? So this relationship is fine. Look at this relationship here, like this. That also is fine. What does an increase in RC do? Increases this product and will causes an increase in AV0. What does an increase in R0 do? RC do? Increase R0. So all the relationships are captured in this diagram. Right? All the relationships are captured in this causal diagram. What causes what? So my output variables are known: Rn, AV0, and R0. These are the output variables. And then I'm looking at the input variables. Input variables are IC and beta and RC. And I'm seeing now how do they affect. What is the mechanism? How do they affect? Right? How does the input affect the output? And capturing it in the form of a diagram. So now, if you look at, can you see the this thing here? the trade-offs? Suppose somebody asks for more Rn. What is your choice of more Rn? Huh? So two choices of increasing Rn are there. One is, so suppose you could increase beta. Do you lose anything? Look at the diagram. Do you lose anything? So many times you would have heard, right? A transistor with a higher beta is very useful, right? Why is it very useful? Why is a higher? If you look at, so many times, you ask students and all that, they're not able to answer this because in the expression for gain, there is no this thing. There is no beta. Why is beta useful? Gain doesn't affect the beta. You can set any value of IC, any value of RC, but you will see in a minute why beta is so fundamental to once you have a diagram like this. For example, all right, so and a higher beta can give you higher Rn, correct? You all realize higher beta can give you higher Rn. Can higher beta give you higher AV?
Yes.
How?
Because beta is the ratio between collector current and the base current. So a high beta indicates higher amount of collector current flowing with a minimal IV.
Higher. So the question is, can higher beta give you higher gain without compromising, let's say, input traces and output traces? The answer will not be obvious to you. But look at that. Suppose I have a higher beta. So a higher beta, what will it result in? A higher Rn. But I want to keep Rn, let's say, same. So what will I do? So what I want to do is I want to increase the gain through what? Through beta. So without disturbing anything else. Is that possible? Well, yes. Suppose I have a higher beta. I take my transistor out and put in another transistor with a higher beta. Not changing for a moment. So higher beta will cause higher Rn. But I want to keep Rn, let's say, the same. So what will I do to IC? I will increase IC. So this will keep Rn the same. Now increase IC what will it result in? Higher IC RC drop and higher AV0. So what I have done is Rin remains the same, R0 remains the same, but I managed to increase AV0. I've managed to increase AV0. Okay. Suppose I have higher beta. Can I get lower R0 without disturbing my Rn and AV? Higher beta, will it allow me to get lower R0? So higher beta will allow you to get higher Rn, but you keep Rn the same, so you will increase IC. But increase IC will cause higher value of IC RC. So what I can do is I can lower the value of RC to keep IC RC the same. So it's the same gain, and lower value of RC results in lower R0. So are you seeing that there is a connection now? The moment you draw a diagram like this, there is a path. Whatever path that I can directly now, this interconnection I can directly affect R0. You're seeing that I can reach R0 through beta. So beta, if you have a higher beta, you can use it to get higher input resistance, or you could use it for getting higher gain, or you could use it for obtaining lower output resistance. Higher beta is allowing you to get everything. Whatever you want, it's allowing you to get that. Higher gain, higher input resistance or lower output resistance. Is that true with the other variable? You would say no. See, suppose I could not increase beta. If you cannot change beta, if you cannot alter, what control do you have in your circuit? You have IC or you have RC. Suppose beta you cannot alter, so you have IC. So let's say you increase IC. So if you increase IC, what will happen? Yes, this IC RC product goes up and then AV0 goes up. But what do you lose? You lose Rn. So you've lost something, right? With increase in IC. Or suppose that so you say, okay, I don't want to use IC, I want to use RC. So if you increase RC, yes, you can increase this and you can increase again, but what do? You lose R0. So you end up with the problem. If you try RC, then you'll end up with a problem. If you try IC, you end up with a problem. But if you try with the beta, you don't end up with a problem. With beta, if you have higher beta, you can get any of these things. So you can capture all the trade-offs that are there in a diagram like this. And I'm sure these kinds of things, when Sedgwick and Smith is writing, he's not writing all this. Cannot write it, because that there's a path from beta to affect R0 and a path to affect AV0, and all that is not being captured in this this discussion here. You're not able to see this. But the moment you draw a diagram, look at what you're able to see. Beta is a key parameter. With beta, you can do now higher beta and all that. You can really, if somebody gives you better and better beta, you can make better and better amplifiers. But that's not true with IC and RC. You will be caught in a problem. With IC, you will increase the gain, but you will lose input resistance. With RC, you will increase the gain, you lose output resistance. Something or the other is going on. You're losing. Not with beta. But then now you say, okay, so but if you go now, if you draw a causal diagram for a transistor, BJT, then you will see that in a BJT, if you try to design and you try to increase beta, that BJT, you will have a loss. Something else will go away. You will start losing something in this. So I've just drawn a causal diagram of a amplifier. In that amplifier, beta is an input. But if I were to draw and couple it to a causal diagram for a BJT, you will see an increase in beta will cause decrease in something else. You'll see all the trade-offs that are coming in. That are there. Okay, so by the way, a diagram, a causal diagram, if I draw and share it with you, you'll have a little bit of a problem understanding. So the best thing is to draw your own diagram. Don't take somebody else's diagram. You use your own, whatever circles you want to place them here, there, outputs and all that, and you draw. Because a diagram which is drawn by you, you will understand better. Rather than somebody else's diagram, you will try to, figure it out, why this, that, and all that. It will be a little bit difficult. So get into a habit of whenever you want to understand something in a deeper manner, the mechanisms, why something happens, how something happens, develop a habit of taking the key variables that are there and tracing the relationship. Draw diagrams like this. It would help you in many, many fields. Why something happens like this, why. And you may be seeing, once you put it in a diagram like this, you will see some hidden relationships which you had not noticed. That's what I'm trying to illustrate to you. The importance of beta and how through beta you can, do all of that. It's not obvious simply by looking at the equations. You will begin to see new things once you draw a diagram like this, a causal diagram like this, because you're seeing all the interrelationships in a small compact place here, and you can see the all the connections and all that. A text is not a very good way of describing it. By writing in a long text, oh, this does this and this does this and all that, you are not able to see the relationship. But in a causal diagram like this, you can see.
Sir?
Yes.
In that causal diagram, why are IC and beta not connected?
Why are IC? Because they are two independent. Beta doesn't affect IC.
Beta is the ratio between IC and
No. Beta is the ratio of IC and IB, but beta is IC and IB, right? But beta doesn't depend on IC or IB. Beta is an independent parameter. What this relationship tells is, if you put, actually this relationship is, how you write is causing you confusion. You are writing, that's an interesting point. When you write beta equal to IC by IB, right? You are thinking beta is affected by IC and IB. If I write this, IC is equal to beta times IB. Then what you're saying is IC is affected. If you apply a certain IB, IC is beta times IB. Beta doesn't depend on IC and IB. First order beta is a device parameter. If you put 1 microamperes, beta is 100, you get 100 microamperes. If you put 1 milliamperes, you get 100 milliamperes. It's not being affected by IC. It's not being affected by IB. All right, so don't look at like this. This is a wrong way of looking. Beta is affected by, beta is a ratio of IC and IB, so beta is affected by that. No. IC by IB is a constant, first order. If you go into the more details, then there's an issue, beta may become first order, the ratio of IC and IB is constant. Right? All right, let me come to the main, this is all the background that was there. The main reason why I'm introducing this is here. Look at this PN junction. So I've taken a PN junction, both sides symmetrical to make it simpler. P is also 5 times 10 power 16, ND is also 5 times 16. Long, both thick P and N regions. And I'm showing you all the currents at this point, at one edge of in the PN junction. So total current that is flowing in the device, 1 ampere per centimeter square. At this point, what is the whole current? 0.41 ampere per centimeter square. And I'm also telling you this whole current it has both, whole current will have diffusion and drift, but the diffusion component is 600 times larger than drift component. So you can say the whole current is predominantly diffusion. At the same point, the electron current is 0.59. Electron current is what? Majority carrier current. Whole current is what? Minority carrier current. Majority carrier current is 0.59 and minority carrier current is 0.41. Now if I break the GN into two parts, the diffusion component of GN is minus 0.86 and the drift component is 1.45. Just take some time to digest this. This is what is happening at the edge of the depletion region. If you were to calculate all the current components. Now, if you're saying maybe this is happening only here, what about here, somewhere else? Well, let me show you a diagram somewhere else also. This is at one diffusion length away. A little bit far, one diffusion length away. Total current is still 1 ampere per centimeter square. The whole current is 0.15. The electron current is 0.85. The diffusion component of electron current is minus 0.315. Drift current is 1.165. So, if you look at this diagram, or if you look at the previous diagram, right? Either way, is the dominant current a minority carrier? Is the dominant current in the PN junction minority carrier? A minority carrier is how much? 0.41. And majority carrier is how much? 0.59. Majority carrier current is larger than minority carrier current. Right? It's larger than minority carrier current. Okay, that's one. So obviously current is not minority carrier current. Majority is larger than this. Is the current diffusion? Well, start looking at the diffusion. Diffusion component is what? One component of diffusion current is here, 0.41. If I just look at diffusion current components, one is 0.41, the other one is, so what is the net diffusion current? Minus. The net diffusion current is minus. So how can it be, how can you say the current is diffusion current? And what about the drift current? The largest component in all these currents, what do you see? So now, if you look at this picture, there's no mistake in this picture. If you look at this picture, you'll say current is dominated by majority carriers and current is dominated by drift. But what is being said is just the opposite. Current in a PN junction is minority carrier current Current in the p-n junction is diffusion. What is going on? I can calculate, I'm just showing you current components here. I've taken a symmetrical, I can do the calculation here, wherever you want, I'll do the calculation. It will be similar. So don't worry about that I've specifically chosen something to mislead you. That's why I've drawn this diagram also. So my point is, majority carrier current is larger than minority carrier current. Drift component is largest component, yet we say current in a p-n junction is minority carrier and due to diffusion. How do we resolve this?
At the junction, diffusion is more than
No, we're at the junction only here. I'm looking at here. At the center, in fact, if I calculate diffusion and drift are same. They are balancing each other. They are almost cancelling each other.
But when we are calculating, we are saying that at junction more diffusion is.
No. Okay, more means what? If I look at this point, the current will come out to be at the junction. Current will come out to be 10 power 4 maybe, and let's say whole diffusion current, and the drift current will come out to be maybe 9.999 into 10 power 3. And at the center, there's no concept of majority and minority. And that's not how you calculate current. You never calculate currents in the center. In fact, within the junction, you have more of almost like an equilibrium kind of situation. So where is the idea of and in the center, as I said, those kinds of issues that are there. So where is the concept of majority, minority? Why is it coming? Why are people saying it? What is the reason that they're saying this? You will see the answer if you draw the causal diagram. How is the current flowing in a p-n junction? Draw a causal diagram of this. Okay, so this is what let's do. How much time we have? Okay, fine. So let's do a causal diagram here. Okay, so let me start by causal diagram by putting here change in diode voltage. Let's put a ground here. Let's build the causal diagram. Diode voltage. Let's suppose I apply it, I increase the diode voltage. So or let's say a given diode voltage, right? A given diode voltage will cause a certain amount of current. What does this diode voltage do? We are looking at mechanism. How does the diode voltage, initially let's say the diode voltage was 0, now you apply 0.7, right? So a certain amount of current flows. How does the diode voltage cause a current to flow? What does it do? We are looking at causing. What does the voltage immediately cause? What does it do? Huh? What does the voltage immediately do? If you increase the voltage, decrease the voltage, what does it immediately? What is the first step that it does? Huh? Depletion width will change, yes. Barrier will change, right? Barrier will change. But what does the change in barrier do? It changes the carrier density here and here immediately. So what I can do is, what it does is delta P xn. And what will it do is plus. And what it will also do is increase delta n at minus xp plus. So if you're looking at mechanism, a change in diode voltage, I have not written in between, you're right, a change in delta Vd will change the barrier. I've not written the barrier, I've skipped the barrier. If you want, you can write the barrier also. Will cause the barrier to decrease, and that causes an increase in carrier density at these two. Correct? Okay. What happens to this? What does this do? And so you get an increased whole current here at this. So whatever happens to delta P, same thing happens on the other side also. Okay, so you get an increased hole density here. What do these holes start to do? The holes will start to diffuse and will give rise to a diffusion current, right? So I can put here, what does it do? It will put here plus and will cause a whole diffusion current to start flowing, JPX. Holes will start diffusing. And of course it will contribute to current, because if I'm looking at current, let me look at current what? See, the current is DC, so you can, if you sum up all the current components at any place, you will get the DC current. So I'm going to focus my attention at Xn. If I sum up all the currents at Xn, I will get my total current, right? So JP, it will cause a JPXN to increase. So a change in VD will increase the hole density at the edge of the depletion region. That will cause a hole diffusion current to flow. But then, this is what we had discussed. The moment the holes are here, what happens? This is a neutral region. So what happens? Electrons also come in. Electrons also are like this. Delta P, if it's neutral, then delta P is equal to delta X. So if there is a hole diffusion current, then there is a, what will happen? There will be a electron diffusion current also. Who's causing the electron diffusion current to flow? Why is the electron diffusion current flowing? What is the driving mechanism? You have injected holes into the region, right? You injected holes into the N region, but that N region is neutral. So the moment you inject a hole, electrons also come into picture. But why are electrons coming? They're coming in response to the holes that have come here, right? They're coming in response to the holes that have come here. The electrons also come in, and it's neutral. So delta P is equal to delta N. So electron density is also going like this. So in which direction will the, a diffusion current will flow, but what will be the direction? Negative. Diffusion current will flow in this direction. It will be negative. Magnitude will be plus, but it will flow in the opposite direction. So electron diffusion current starts flowing. Right now here, what happens here on the, we'll come to this. So there is a JNXN also starts flowing. So now note that if I say the JNXN is larger than JPXN, which will be true, you agree with that? The magnitude of the electron current or diffusion current will be more than the, by the way, I should write here diffusion. These are also diffusion component. The magnitude of the electron diffusion current would be larger than hole diffusion current. Why? Because Jn is dn del n by del x, and Jp is q dp by del p by del x. Diffusion constant of electrons is higher than diffusion constant of holes. So more diffusion current flows. But what is the source of the diffusion current? What is causing that electron diffusion current? It is this. If this were not there, it would not flow. Note the diagram. This causes this and this causes this. The arrows are important here. Okay, arrows are important. Yes, diffusion current, electron diffusion current flows, but what is causing it? So similarly, I can write here Jn xp. What is the nature of this current? Diffusion on this side. And this is equal to Jn. Because note that there is a diffusion current, right, on this side. Where will it come from? The electrons on the p side, where does it come from? It comes from here. So this is the source of Jn xn. So Jn xp. Note that Jn xp is a diffusion current, and that causes Jn xn at this one here. And this Jn xn and this Jp xn, they sum up to give rise to the total current, J total. And this Jn xn and this Jn diffusion give rise to JN, XN, drift. Again, the arrows are important. How things are happening. What is causing what? Let me show the same diagram in now in bigger ones here. Whatever I've drawn, I've shown it in here along with numbers. This is what is happening. Again, let's understand. Change in this is like diode voltage, VD. Diode voltage. What does it do? Increases the hole density and electron density. What does it cause? Diffusion current to flow. That contributes to total current. But this one causes electron current to flow. On the other side, there is a diffusion current. That causes the electron current to flow. Try to understand this and look at the full picture here. And look at all the current components I've also written. Final current is 1 ampere per centimeter square. It's made up of what? 0.41 of diffusion current and 0.59 of electron current. Let's address the issue of majority versus minority. Let's look at the current. 1 ampere per centimeter square made up of 0.41 of hole diffusion minority current and 0.59 of majority carrier current. But okay, fine, so this is a minority, but who is determining this majority carrier current? How much this number 0.59 will be? Who's determining it? Look at the arrow. Who's determining this? A minority carrier current on the other side. On the, this is the PN junction that we are drawing, P and N. And we are looking at one particular point. We are summing up the currents at one particular point. So we are looking at, okay, what about GN? It's a majority carrier current, but who's determining this 0.59 majority carrier current? Is the minority carrier current on this side. That's what is determining it. So then, if you say total current is 1 ampere per centimeter square, 0.41 is minority, 0.59 is majority, but who's determining this majority is also minority on the other side. Right? So the correct statement is current in a PN junction is not minority carrier current. The correct statement, what would you like? Current in a PN junction is determined by minority carrier current components. Is determined by. It's not equal to. Because if I look at equal to, if you say, then 0.59 is higher. 0.59 is higher than that. So current in a PN junction is not a minority carrier current and all that. It's determined, that's very important, it's determined by minority carrier current components. That's a more accurate way of saying it. Would you also say that the current in a PN junction is determined by diffusion currents? This is obviously a diffusion current. And this one is not a diffusion current, but is determined by diffusion component. So current is again determined by diffusion current component, determined by. If I look at the net total current, the current components, the highest current component is here, drift. Yes, the highest component is 1.45, even larger than the total current. Drift current is even larger than total current, 1.45. Yes, it is. The dominant component is drift current component. But what is it determined by? Even this drift current, if you look at the arrows, what is it determined by? If you look at the arrows, who's determining the drift current? This value of 1.45 that you see is coming from, one root is here, diffusion, the other root is diffusion. It's determined by that only. Right? So it may be a very large component, 1.45, but that's not determining what is happening here. So a causal diagram like this, if you trace the connections and see what is happening, will let you know, a diagram like this will let you know why are we saying current in a PN junction is diffusion current, or diffusive limited, or is limited by minority carrier current components. Why are we saying it? Even though the largest component at any particular point is drilled outside the depletion region when I calculate. Right, so these drawing of these diagrams here will help you understand, you know, wherever the question is, why does something happen in a certain manner, how, especially how does it happen, what is the underlying mechanism. So looking at what are the key variables and tracing the relationship, drawing these diagrams and putting it all together in one place will help you understand these things in a lot more, a lot better than simply writing equations or text and things like that. Capturing it in the form of a diagram like this can be very helpful. So whatever project you're doing, whichever course you're drawing, maybe whichever course you're taking, start sketching diagrams like this and see whether it helps you. Causal diagrams. Whether it's a course on you know, device or circuits or whatever it is, see whether diagrams like this help you. Also, it's a good way to revise. Once you have you know, read something, let me think about, and whatever I've understood, let me draw it out. And if you're able to draw out all the relationships and all that, maybe you have a good understanding. That is it. All right. Any questions before we wind up?